Well, hello there, everybody. Mathman again. And in this video, we're going to take a look at a couple of things. We're not done yet with exponents and logarithms. One thing that we hadn't proven, we had only taken it by as a given, is that x to the 0 is 1, or any number to the 0th power is 1. Well, we're going to demonstrate how that works, why that is, in a pretty simple way, pretty intuitive way, using the laws of exponents. We're also going to do a little graphing, again, testing my artistic skills. At least I'll try to do the best I can at graphing these points and showing you the general behavior of exponential functions and logarithms. And maybe we'll take a look at some other problems also. This will be sort of a miscellaneous video. So with that, here we go. Now with this last video, I had put up the 6 rules that we had put up. I guess we could add a 7th, where x to the 0 equals 1. And we hadn't shown that, we hadn't demonstrated that, had we? So let's erase this board and go through the reasons why. This stuff, you can't leave it on there too long. It's been on there for several hours, and if it's on there for too long, it has a tendency to dry almost permanently on the board. Okay, try to get the screen on there. Okay, so we're demonstrating x to the 0 equals 1. Well, what if we had n to some power p? Well, that's always the same as n to the p plus 0, because p plus 0 equals p. So, by our law of exponents, this is the same as n to the p times n to the 0. And this only makes sense if n to the 0 is 1. So there you have it. That's the way we demonstrate that n to the 0th power is equal to 1. So QED, n to the 0 equals 1. Gee, you thought probably I was going to be going through some great big lengthy deal. I probably should have done that in the very beginning, but I didn't notice it in my notes until just recently, and so I thought it would be good to put that up. Now, what do we, well, we have these functions, exponential functions. Oops. You know what I got to do? I got to make this so that it doesn't shift. And I'm going to do what I did with this. That I think will help. So we'll just okay. And this little notch, I'm going to have to narrow this down a little bit so it doesn't stick out over the edge. And then we've got, we'll just do this. All right, so we have our xy coordinates. This is x, this is y, and we got 0, and we got x equals 1, 2, 3, and we got 1, 2, 3, 4, 5, 1, 2, 3, 1, 2, oops, I didn't do such a hot job there. And we try to fix that. Okay. 3. They're sort of even. Now, let's say y, we have the function y equals e to the x. So, when x is 0, oh, let's do negative 1. Hey, you know what we're going to do? We're going to go 2 to the x. All right. Let's try y equals 2 to the x, base 2. And so we have y, let's try it. I'm sorry. We have x equals negative 2, negative 1, 0, 1, 2, and we have y equals 2 to the x. So y is 2 to the negative 2, that's 1 over 4, so that's 1/4. This one's 1/2, and this is 1, this is 2, and this is 4. Okay, so when it's negative 2, here's negative 2, we're at 1/4, so that's 1. It's probably down around there somewhere. When it's 1, it's at 1/2. When it's 0, it's 1. When it's 1, it's 2. And when it's 2, it's 1, 2. It's 1, 2, 3, 4. So we have 2, 4. And we can see the general pattern. I make little dots because I can't draw lines very well, but you can see the pattern. It's sort of like this. It's a smooth curve though. Mine isn't smooth. You see, my hand doesn't hold steady, but it's kind of like that. It never gets to 0, but it gets close to 0 when the negative x, when negative x is large. We have a large negative x. It's very, very close. 2 to the x is almost 0. It never gets to 0. We say it asymptotically approaches 0. Only when x is infinity, and x never gets to infinity, is the function 0. And when x gets big, in the positive direction, when x is big in the positive direction, it gets big, very quickly. So we have a function that makes this curve like that. And when it's 0, y is 1. All exponential functions behave this way. Okay. So that's what we have for 2 to the x. Now, when we have 2 to the minus x, when it's the opposite, when it's in the opposite direction, then you know what we're going to do? I'm going to make these less pronounced so that they don't show up as prominently. So we'll just redraw our x-axis. And our y-axis. All right, so we're going to say 1, 2, 3, -1, -2, -3. Get rid of this sloppiness. And we can say this is 1, 2, 3. Okay, and what we want is y and is equal to 2 to the negative x. So let's make a table. X is -2. X is -1. X is 0. X is 1. X is 2. And y equals e, or I'm always tempted to do e. 2 to the x. Okay, so this is negative x. So 2 to the -2 is equal to 2 squared. So this is 4. 1, 2, 3, 4. So we got, we're over here somewhere. Okay, so that's 4. Now we have 2 to the 1, -1. So 2 to the -1 is equal to 2 to the 1. So that's 2. So for 1 minus 1, we have 1, 2. So it plots right there. When it's 0, it's 1. So 0, it's 1. And when it's 1, it's minus 1/2. So it's down here. Let's see. I'm sorry. When it's 1, 2 to the minus 1 is equal to 1 over 2. So it's 1/2. Sorry, I got myself distracted by my phone pinging. It's been doing that all day. 2 to the minus 2 equals 1 over 4. So that's 1/4. So that's about here. And what we see is sort of the mirror image of the 1/2 and 1/4. So what we have is a function that approaches 0 in the positive x direction, and we have a function that when you go into the negative x's, it goes up steeply. So you end up with a curve like this. And it asymptotically goes to 0 as positive x goes to infinity. Oops, that's not a very good infinity sign. And it goes to infinity, goes to infinity, it goes to 0 as x goes to infinity, as x goes to negative infinity. So it goes to positive infinity. So we have a very steep curve that goes up that way, and so it's just a mirror image of e to the negative x, or e to the x, or 2 to the x. 2 to the x, remember, was just the opposite. It goes through there, 2 and 4 and 1 and 1/2 and 1/4. And so we have this is 2 to the x, and that's 2 to the negative x. Now, what if it was y equals minus 2 to the x? Well, then we have x is minus 2, minus 2, minus 1, 0, 1, 2, and y is equal to minus 1 on 4, minus 1 on 4, minus 1 on 2, 1. This is minus 2, minus 4. I gotta go turn that off, so hang on a minute. Oh. Sorry about that. So when we have minus 2 to the x, everything is negative. So we have minus a quarter, minus a half, 1, minus 2, minus 4, and we see that it goes like that, and that's y equals minus 2 to the x. So we got several different ways that it can plot, just so that I'm not the best drawer again. So that's y equals minus 2 to the x. So it goes sort of like that. And we can do the same thing for logarithms. Remember, well, let's see if we can get ourselves an axis. You're on here. And what I did was I tried to stick some Gorilla Tape on there to make it so that it doesn't slip on this board when I hold it. And it seems to work a little, except the Gorilla Tape is a little fat. All right, so we got our x, we got our y. And we got 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1. Whoops. I should have gone a little more steeply. This is more like 1, 2, 3. Okay. Let's say that we have a base 2. 2 to the y equals x. All right. And so we have, let's say y is 0, 1, 2, 3, 4. And so x is equal to 1, 2, 4, 8, and 16. And what we have is y equals log base 2 of x. So we have log 2 of 1, log 2 of 2, log 2 of 4, log 2 of 8, log 2 of 16. Well, let's say these are 2, 4, 6, 8. We can, let's say these are graduated in 2. So this is 2, 4, 6, 8, 10, and so on. Okay, so y is 0. we have when we have y equals log 2 of x, when x is 1, 2, 4, 8, 16, y is 0, y is 0, 1, 2, 3, and that's 4 for 16. So when x is 1, so that would be right there, y is 0. So you got right there, right in that spot. Okay, when x is 2, y is 1. When x is 4, we have, oh, wait a second. We're making these graduated too also, so that's 2, 4, 6, 8. Okay, so when that's 1. All right, x is 2, y is 1, so right there, about. When x is 4, y is 2, so right there. When 8, we have 3, which is about there. And 16, x is 16, so that's 10, 12, 14, 16, somewhere out here somewhere is 16. Y would be 4, so it would be up here. Now, we can smooth it out. Oops, that's 3. So, okay. Now, when x, we start approaching 0. Okay, as we approach 0 here, we start getting into fractions. But we didn't make room in our table for these fractions. So let's make another table. And we have y. Oops, I used the different color pen. Okay, let's make our table so that we have between 0 and 1. So let's have our fractions be 0.125, 0.25, 0.5, I don't know, 0.75, and let's see where it takes us. So x is then, let's just simplify our calculations by using the handy calculator. So we have 0.125 log base 2 equals minus 3. So this is minus 2, minus 4, minus 3. So 0.125 would be really close to there. So we're there. 0.25 base 2 equals minus 2. So for the 1/4 right there, it would be right there. For 1/2, it's 1. And so what we see is we go down like that, and our curve starts taking a shape like this. So it's sort of like this. I didn't do a very good job of drawing it here, but maybe I can wing it by eye. Starting here, we can go sort of like this, and sort of like this. And I didn't draw that very smoothly, did I? Oh, I'm not a very good freehand artist. But it goes sort of like that. And maybe it shows up a little better on the camera than by eye. So this is y equals log base 2 of x, or really base of anything x. They all behave pretty much the same. We can do it with negative numbers, and it'll be similar. It'll be something of a mirror image of that. So we would have something like that, or kind of like that. It doesn't curve up as much. And again, these are functions that plot forever. As big as you want to make this, it'll continue to plot. There's no end. So we've taken a look at some of the plots of our exponentials. Why don't we try and solve a few problems, and we'll take a look at what we've got here. Well, what if we want to change bases with logarithms? So why don't we take a look at a specific problem, and we say we have b to the log base b of x is equal to x. Well, we want to change the base. So if we take log a of this, we have log base a of b to the log base b of x equals log a of x. But then we have log b of x times log a of b equals log a of x. So therefore, log b of x equals log base a of x over log base a of b. And that's how we are able to change bases. using logarithms. Now, let's say we start with a problem such as this. A squared a to the 7th over a to the minus 6 all raised to the 1/5 power. The problem is to reduce this into the simplest form. Well, this is basically 1 over a to the minus 6, which is 1 over a to the 6, which is equal to a to the 6. So now we can put that in the numerator, and this is a squared times a to the 7th times a to the 6 to the 1/5. Well, now we can use the law of exponents, and we've got a to the 2 plus 7 plus 6 to the 5th. That looks like a 9. So that is equal to a to the 13, 14, 15, a to the 15 to the 1/5. But our other law of exponents says that this is a to the 15th times 1 over 5, and that's equal to a to the 15 divided by 5 equals a to the 3rd. And that's our answer. So all of that mess just reduces to a to the 3rd. Now, let's take a look at another problem. They've given us 8a to the minus 3 to the minus 1/3. That's not a very good bracket. Still not a very good bracket. There we go. Now, we want to reduce this into simplest terms. Okay, so basically this is, if we recognize, this is 2 to the 3rd, 8. 8 equals 2 to the 3rd. And that is over a to the 3rd to the negative 1/3. So this is equal to 2 to the 3rd times negative 1/3, and this is a to the 3rd times negative 1/3, and that is equal to 2 to the negative 1 over a to the negative 1, and that's simply a over 2. And that's our result. Let's take a look at another one that they've got. We've got a squared over a squared plus a to the 4th. Well, remember, here we do not have a multiplication, so we can't add exponents. So we can't, what am I writing? We can't have, let's say, there, no law of exponents. Okay, so what do we do in this situation? Well, we can factor out. So what we have up here, we have a squared. We have a squared up here. And we can factor out a squared down there. A squared times 1 plus a squared. And these cross out, and that's 1 over 1 plus a squared. We could do more with this if we wanted. We could say, well, I don't think that is necessarily simplifying things, so we'll just leave it at this. So that's the answer. In fact, that's the solution to the problem. So we've seen a few problems with exponents now. Let's see if we have other problems. Okay, why don't we take a look at this? We have, this is an interesting one. We have a squared b to the third times a to the fourth b to the ninth. And this is all to the third. Okay, so how does that reduce to the simplest? Well, here we have different bases. And unless we find b to the n power equals a, we wouldn't be able to convert that over to a. Theoretically, we could. And we could say that b equals a to the 1 on n. And then write, we have we have a to the 1 on n to the ninth, which is equal to 9n a to the 9n. But you know what? We don't have that, and we're not going to do it that way. I mean, technically we could, but we're going to leave that in base b. But we can't add these exponents because we have different bases. But here we have bases that are the same. So why don't we take a look at what we can do to simplify. So we have a to the 2 plus 4, and we have b to the 3 plus 9 to the, what is it, 1/3? 1/3 third power. And that's equal to a to the 6 times b to the 12th to the 1/3. And that can be reduced to a to the 6 divided by 3 times b to the 12th divided by 3. And this is a squared times b to the 4th. And that's, we can leave it that way, or we could do it this way. A b squared squared. I don't think it's necessarily simpler that way. We'll just leave it this way for now. So just a little testing of our knowledge of exponents and how they work. Let's see what other problems we have here. Now here's an interesting problem. Let's say we have a to the fourth plus b to the fourth, or yeah, we can make it anything, in 9 to the ninth, all raised to the 0. Well, that's simply, this whole thing is just a to the fourth plus b to the ninth is some number n. So this is equal to n to the 0, which is 1. We have to be careful with this. We may be tempted to say a to the fourth times 0 plus b to the ninth times 0. Why isn't that correct? Well, because we have that addition. Now, if this was multiplication, a to the fourth times b to the ninth to the 0, then we could say that's a to the 4 times 0 times b to the 4 times 0. And that, again, is 1 times 1 equals 1. So in that case, it would be. But we have to be careful here. We don't want to be tempted, because if what we might do there then is say 1 plus 1, and that's 2. And that's wrong, because the whole entity is raised to the 0, and that anything raised to the 0 is 1. So we have to be careful about our exponents. And we can be fooled if we're not careful. So let's see what else we've got. Okay, now we've been given an interesting problem. We've been given a problem where 4.7 raised to the 1/3 is equal to n. And we're to find n under the condition where 10 to the x equals 4.7. So if 10 to the x equals 4.7, then we have 10 to the x to the third equals n. So we have 10 to the x on 3 equals n. And then we have log of this base 10. So we have x to the third equals log of n. And x is equal to base 10 log 10 n to the third. All right, so what we have to do is we have to find what x is. And then we can find, well, this is the best way to go about it. We'll leave it right there. And we'll keep that. And we've got 10 to the x equals 4.7. So we know x, 10 to the 0 equals 1, and 10 to the 1 equals 10. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5. So 4.7 is right there. So what value do we have? Okay, so we got to pick a value that's somewhere in between 0, 0, and 1. And that's somewhere, let's say, that's 0.47. Let's try 0.4. We can guess. So 10 to the 0.47 equals, let's give that a shot. I think it's going to be too big, but let's give it a, okay, 10 to the 0.47 equals 2.9, 2.9, so it's too small. So if we have 10 raised to the 0.5, we have 3.16. 10 to the 0.5 equals 3.16. 10 to the 0.6, let's give that a shot. 10 raised to the 0.6 equals 3.98. We're getting there. So it's bigger than we thought. All right. 10 raised to the 0.75 equals 5.6. That's too big. 10 raised to the 0.7 is 5. So it's try 10 to the 0.65. And let's give that a shot. 10 raised to the 0.65 equals, we got 4.467. Now that's pretty close. Let's try 0.691. 10 to the 0.691. Now that's too big. So we'll leave it at 0.69. So we have x equals 0.69. So here we have x is 0.69. 0.69 on 3 equals, and we'll erase this, equals log base 10 of n. So 0.69 is 3.2, and that's 609,390. So it's 0.23. 0.23 equals log base 10 of n. And then 10 to the 0.3, 23, 10 to the 0.23 equals n. So let's see what that gives us. 10 raised to the 0.23 equals n equals 1.69. So 4.7 to the third equals, should be 1.69. So let's see, 4.7 raised to the 0.33333. Well, this point is 1.68. We were close with our guess. So, I mean, we could have just calculated that directly, but we used some interpolating in base 10, given this information, and then using that to find a solution for n. So it was an interesting problem. The thing about these exponential problems is that we often don't get exacting solutions. Okay, here's one that we can look at. 3 to the n equals 2 squared over 3 squared. So basically we have 3 to the n is equal to, all right, that's 4 over 9, and 4, well, that's, yeah, we can leave it that way. If we take log base 3 of 3 to the n equals log base 3 of 4/9, n equals log base 3 of 4/9, and 4/9 somewhere close to a half. Let's see, because 5/10 is a half. Okay, 9 into 40 goes, let's see, 4 is 36, 5 is 45, so 4, 36, we got 4, 4, and it just goes on, 4, 4, 4, 4 equals log base 3 of 4.4444. Okay, so if we have 3 to the x, and we have x is 0, now let's say x, we'll write it over here. We have x is 0, and we have 3 to the x is 1, and we have x is 1, and we have 3. Okay, so we're somewhere, n has got to be in here somewhere. N is in between 1 and 0. And so 3 to the n equals 0.4444. And that is between, well, let's see, 3 to the n, yep, is 4444. So we need a small number. We need a very small number because we need something between 0, 0 and 1. And this would be 3, and this is 1. 3 to the 0 equals 1. So we need a fraction. We need 3 to the x equals 0.4444, and 0 is too big. So let's try minus 1, and that's 3 to the minus 1, which is 1/3. 3 and 2, 10. That's 3, 9, 3, 3, 3. So minus 1 gives us 0.3333. So it's between minus 1 and 0. So this is 0.3333, and 0 is 1. So that's our n is between -1 and 0. And so we've got to find a value. Let's try -0.5. -0.5, or -1/2. -1/2. So that's 3 to the 1/2 negative. So that's 1/3 to the 1/2, or 1/√3. Square root of 3 is 1.4, that's 16, 4, 5, 4, 1, that's 6, 9, 1.96, no, 1.7, 1.7, that's 49, 11, 7, 1, 9, 8, 2.989, so it's not 1.7, 1.8, 1.8, 64, 8, that's 14, 18, 4, 12, 3.24, so that's too big. So it's 1.7, let's say 2, 1.72, 4, 14, 3, 14, 49, 50, 7, 12, and that's 2, 7, 1, 4, 8, 5, 9, 2.95. So it's about 1.73. Let's say 1.73. Let's try 1.73 squared and see what we got. 1.73 times 1.73. Yeah, that's pretty close. So it's 1.73 is 2.993. That's pretty close. It's 1.731 times 1.731 equals, well, it could be bigger. So anyway, that's 3. We're going to say it's 1.73. Okay, we're just going to leave it at 2. 1.732. So this is 1 over 1.732. Okay. 1. Okay. 3. All right. 1 divided by 1.732 equals, that's equal to 0.57736. Okay, so that's 0.57736. It's too big. We want 0.4444. So it's got to be somewhere between -1 and -1/2. All right, so -1/4 is too small, I would say, or -3/4, -3/4. Shall we try that? Okay, 1. So that's 3 to the -3/4, which is 1/3 to the 0.75 is equal to 3 to the 0.75 is equal to 3 raised to the 0.75 is 2.27951 invert, and we have equals 0.438. So we're closing in on it. It's not quite 0.75, so that's 0.438. So it's got to be bigger than 0.75. So let's try 0.76. 3 to the 0.76. Let's give that a shot. 3.76. And we take the invert. Still too small. 3 raised to the 0.77 invert. 3 raised to the 0.74. Here we go. 3 raised to the 0.73. Invert. Yeah, this 0.72. So it's about 0.72. So x is 0.72. 3 to the 0.72 is 3 raised to the 0.72 is, and then we invert. That's too big. 3 raised to the 0.725. Still too big. 0.3 raised to the 0.3 raised to the 0.73. Well, it's somewhere to the 3 raised to the 0.71. Too big. So it's about 0.72. And so then when you have 1/3 to the 0.72, we're approximately 0.44. Okay, so it's in that neighborhood. So n equals log 3 to the 0.4444, and n is approximately 0.72. So let's see what we got here if I do it correctly using a calculator. So we have 0.4444 log base 3 equals point. It's closer to point negative. I forgot the negative sign here. Negative 0.738. I didn't close in on it well enough, but somewhere in there. The 0.72 gives me 0.44. So that's fairly close given the crude circumstances that we were trying to work it out based on interpolating. Now, let's take a look at another. My timer timed out. Okay. Okay, here's a problem that looks pretty cool. So, if we're given log base b of n equals x and log base b of m equals y, show that this multiplication is equal to x plus y. So, the first thing we need to do is show that m is some power of n, n to the p. So we have log b of n to the p, n equals log b of m times n. So this is log base b of n to the p plus 1 equals log b of m times n. So this is p plus 1 times log n equals log b of pm times n. And this is p log n plus log n equals log b m n. This is log base b of n to the p plus log of n base b equals log base b of m n. But n to the p, remember m equals n to the p. So that is log b of m plus log b of n equals log b of m times n. But that was given. Log of m is y, log of n is x, so we have y plus x equals log of b times m times n. So we've shown it. We've gotten the equivalence there. The corollary problem to this is showing that when we have a division, m divided by n, let's write that, m divided by n is then y divided by x, or I'm sorry, y minus c x n, so y minus x. All right, so how do we do that? Again, we say that m equals n to the negative p, and so we have log b of, well, we just say m is n to the p, so we have n to the p times n, or divided by n, equals log b m divided by n, and this is log base b of n p minus 1 equals log b of m divided by n, p minus 1 times log base b of n, log b of m divided by n. This is log p log base b of n minus log b of n equals log b of m slash n. This is log b to n to the p minus log b n equals log b m divided by n. This is log b of m minus log b of n equals log base b of m slash n. But that is y minus x equals log b of m slash n, and we've proven it. So that was a pretty cool problem. And at this point, it's getting late, and we'll call it quits.